Hi, I'm a design engineer working for Stadium Stontronics, and I want to say a few words about our research into optimization of switch mode power supplies. Recent progress in switch mode power supplies has been characterized by a rapid increase in the efficiency of energy conversion and power density, which are the key criteria in the design of high-frequency power converters and the best measures of their performance. The demand for reduced size and minimization of losses has led to a re-evaluation of the approach to building magnetic components and the selection of power switches, driving the operating frequency to ever higher levels in order to facilitate more compact and efficient designs, such as the one you can see on the right. Nowadays, in order to catch up with or move ahead of the trend, design engineers have to investigate in-depth phenomena associated with electromagnetic fields and frequently utilize thermal analysis tools as in the film here. Thermal qualification is particularly crucial for magnetic components and semiconductor switches. The latter because of their relatively small thermal mass, and the former because of their insulation class and the saturation level of magnetic material used. Magnetic components with an air gap display a distinctive pattern in temperature distribution in windings if measured along the gapped column. This is due to the fringing magnetic field around the air gap. This phenomenon manifests itself in the form of so-called hotspots and can be readily analyzed by the use of infrared thermography as shown here. One can observe that in the vicinity of the air gap, the magnetic flux density in the magnetic domain is diminished. This is due to the fringing effect phenomenon, as the magnetic field lines are no longer entirely enclosed by the core, but tend to enter the surrounding medium. The fringing flux crosses the conductors, inducing excess eddy currents that counteract the useful current, thus increasing the so-called AC resistance, which reduces the overall efficiency of power conversion. These days, when designing new power supplies, this extra power loss is beginning to be a significant factor. The fringing effect power loss is problematic, as it is a function of many variables. For example, the size of the air gap, the cross-sectional area of the core, and the geometry of the windings, as well as the operating frequency. Power supplies engineers are frequently forced to design around the problem by spacing the windings away from the gap or using a so-called Litz wire, which mitigates the effects of the fringing flux. They can also tackle the problem directly by replacing a portion of the core with a material of low permeability, thus forming a distributed air gap, or by splitting a discrete air gap into a number of smaller gaps. These are some of the ways we are trying to optimize our designs at Stadium Stontronics. Thanks for watching.